Hello, everyone. It's taking longer and longer for Zoom to actually connect nowadays. I don't know what the deal is with that. My cat's messing with my stuff. Can't take her anywhere. Yeah, I'm talking about you, Allie. All right. Anybody have any questions before we get started?
Sir, I do.
Yes.
I tried emailing you last Friday about Lab 1, and I was going to try and speak with you about it during lab today, but you said it was canceled.
Okay.
I was wondering.
Yeah, we can talk like after class if it's private, or you can go ahead and go for it now if you want.
Let's do it after class so it doesn't eat into everyone's learning time.
No problem. Thanks, Gavin. If it's just about not having your stuff turned in, I'll just let everybody know. Or if those of you have bad lab grades, I just want to, as your initial lab, let me know if you're interested. You're allowed to resubmit that first lab for up to 50% of the points back. I just had to give y'all a full number of points off for each of the errors so that y'all read thoroughly and see what your errors were and hopefully correct for that. So anyways, do that. And when you do submit the new lab, tell me exactly which lab it is and that you submitted, and I'll go ahead and regrade it shortly thereafter. But yeah, Cadmium, I remember to speak with you at the end of class. You just, if there's still people waiting around, I can put you in a breakout room and you and I go over there separately, or we can talk it out in the main setting if everybody's gone. So anybody else have any questions?
Yeah, I had one for one of the homework questions with vector components.
Okay, yeah, I had a student ask about that too. I'm wondering if it's problems with entering the vector or problems with knowing how to do vectors. So go for it. I've got it where you can share the screen if necessary.
Yeah, I'll put that on there. How? Let's see. Oh, here. There you go. This thing.
Gotcha.
I'm just having trouble conceptualizing what they want for the X component and the Y component, because it's just, yeah, I'm just having trouble wrapping my head around it.
Okay, so leave that up for a second so I can discuss it in real time. I think there's actually supposed to be a way I can mark this up. I haven't figured that out yet, even when you're actually talking. But anyways, I'll describe it as best I can. So this vector n, what we have here is a axis system that's been tilted. And in fact, today I'm going to do an example where you see a tilted axis for just this reason. So the y component of the normal vector will be parallel to the y-axis. So you can imagine it going from the origin up to a place diagonally down and to the right of the tip of the n vector. And then if you go from that spot horizontally, well, parallel to the x-axis to the n vector tip, that's the x component.
Yeah.
Okay, so that makes sense. Can you see that image wise? Imagine a laser beam shooting parallel to the x-axis from left to right. Okay, and now imagine that n vector is a sheet of plywood. We're just looking at the edge of it. Everywhere there's a shadow, that is the y component. Now, if you do the same thing, this is going to be the x component in a different place, by the way. If you do the same thing with a laser beam shooting parallel to the negative y direction and treating n as a sheet of plywood, the x component will be the shadow of the n vector.
Yeah. Well, I mean, I kind of understood that bit, but I was just sort of wondering, like, let's see.
Is it the negative or the positive that bothers you?
Yeah. Like why? So also
well,
the angle being theta, theta being the angle between the vector and the y-axis as opposed to the x-axis, I think.
Right. Okay. Well, let me try to talk to you about it this way. Remember how I showed you your first sort of idea of what a vector is a series of walks that you take out of your front door? And like you
Sure.
might walk due north for 100 meters and then hang a right and go due east for 20 meters and then all this sort of stuff. Well, that has to be true about the components. In other words, you have to imagine walking from the origin or from the tail of the vector that you're talking about along X and Y axes till you get to the tip of the end vector. So in the case of leaving the origin along the Y axis, you're going to walk that whole shadow that I talked about earlier, and then the head would be pointing in the positive Y direction. Now the head of that vector will be at the tail of the X component vector, this one in a different place as opposed to the place that I showed you earlier. Now you're going to walk left as if Y is north, you're going to walk west along that other vector until you get to the head of the end vector. So you can see now that the direction that you walked along that Y, or along that X component vector, was actually to the left, therefore it must be negative. So the components aren't just legs of the triangles, the components are vectors themselves. Really wish.
Okay.
Does that make any more sense?
A little bit more. I think what might have been confusing me was the placement of the theta angle and the like necessitating putting a negative on the X component, because depending on the angle, you could get a negative number out of sine
Yeah,
theta anyways.
Yeah, that's what I've been telling people. I always try to choose the smallest angle, or say the angle from the vector to the nearest axis. And then I always use the signs. I don't want you guys really trying to use the signs of the trig functions, because if you do that, that third quadrant and that second quadrant can really be a bear. Actually, the second, third, and fourth quadrant can all be a problem, but the third is particularly problematic because, for instance, it'll return a positive tangent, and sine and cosine will return positives when it's distinctly negative in both cases. Both the X and Y components are negative for a vector pointing in the third quadrant. So if you always choose the angle closest to the vector between it and the closest axis, then you just have to force the sign. But yeah, you could have just said theta goes from the positive X axis all the way around to that end vector. And then by doing that, sine would probably give you the right component of the right sign, and cosine would probably give you the right sign. But notice you'd have to use cosine for the X component and sine for the Y.
Gotcha.
Okay.
Okay. Yeah, it was just kind of throwing me for a loop a little bit. Thank you.
Josh or Jacob, was this anything related to the question you asked me about? I think I saw at least Joshua was in here this morning, not maybe Jacob's not, but I think they're both here. No questions? Okay. All right, well, let me go ahead and steal the screen back from you, I reckon. So yeah, remember your vectors have to be, so if this is your original vector and you'd say this is the tip, you know, it'd be pointed if it wasn't for the lid. Oh, good, Jacob. So if your vector is like this, then your component vector has to start at the tail and go along one axis. And since it started at tail, that means the head has to be up here. And then your other component vector has to start at the head of that and go along another axis. And then that dictates which way it's going, which direction the head's pointing. So if the head's pointing in the negative X direction, you're going to have to put a negative sign on it. If the head's pointing in a negative Y direction, you're going to have to put a negative sign on it. And that is a really freeing thing, believe it or not, because it allows you to use any angle instead of having to rely on, you know, 232 degrees or some weird crap like that. You can always use angles from the first quadrant, and life's a lot easier. And you know, angles in the first quadrant, sine and cosine, are basically both positive from 0 to 90. So you never have to worry about the signs tripping you up on that. So that's why I recommend you do your vectors that way. Any other questions? I've got like 2, maybe 3 problems I really want to work with you guys today. So we got, you know, ample time basically, but does anybody else have any questions? I see some chats coming up. Let me see if I missed anything. Yeah, Jacob said it did clear it up, and okay. I got you, Jacob. No problem. All right. So looks like we're going to go ahead and move on then. So last time I actually solved the statics problem with you, and I solved the elevator problem. I hope y'all were able to understand the elevator problem, and specifically like with the elevator problem, how you get an apparent weight. You still have a regular weight, you still have mg, but then on the elevator, you have an apparent weight, as you can tell when you actually ride an elevator. And if you take off on the way up, for instance, you feel a little bit heavier and your legs compress. So that's acceleration in the upward direction. But oddly enough, also an acceleration in the upward direction is when you're going downward at a constant speed, and then all of a sudden it starts to accelerate to slow down, right? That's also an acceleration in the upward direction. So again, you feel heavier. Similarly, you feel lighter when you first start to accelerate downward. That's just like falling, right? And that's a downward acceleration. But also when you're on your way up, which is the way most people have recognized this force before, I think, when you're on your way up and it starts to slow down as it gets to the floor, that's an acceleration downward as well. And that makes you feel light as well. So, and really the only difference between solving for an apparent weight that's bigger than your weight and apparent weight that's smaller than your weight, the difference is which direction acceleration is. So when the acceleration in fact is down, you feel lighter, and when the acceleration is up, you feel heavier. So hopefully that makes some sense of it. So let's start off now with really the two last problems of this chapter, and one's the Atwood machine. I chose not with my other classes not to do necessarily an incline plane problem. In your class, I'm going to do it, and then I'll post this on YouTube. By the way, everybody, I'm now posting our videos directly. I'm saving them directly to my computer, so the bandwidth comes off a little better, and you won't get as crappy looking notes. And then I immediately, once they're saved, which takes about an hour after the class, and then sometimes up to another hour to upload it to YouTube, then that video will be on YouTube. So you don't have to wait for the link to actually appear on YouTube. You can just go to, on your Canvas, you can just go to my YouTube channel and see it there, usually within 2 hours of the class meeting. So hopefully that'll help. It'll be, the images so far do look a little clearer. So hopefully that will continue. Also, remember, we've got a test this weekend. I want to make sure you guys go ahead and knock that out. Remember, it's due technically Wednesday, but you get up to 3 attempts. And if you forget about it, you're going to get a 0, and that's not a good thing. So I really want you guys to maybe immediately today, after taking a practice test a couple times, go ahead and take one pop at it. That way you'll have a grade other than 0 on the books, and then you can spend the rest of the weekend and Monday and Tuesday and even part of the day Wednesday making yourself do better on the practice test until you can make a really good grade on that. So let's get started. I'm going to go ahead and turn on my document cam. I still got people coming in. I will let them in as we go along. So I'm going to start off with a common problem that we use in physics, and it's really good because it's a two-part or two-body type problem. So you could, in principle, use a single F equals ma equation, but when you do that, you treat two separate bodies as if they're one body, so you can't find out any information about the force acting between them, because then that's an internal force. And remember, Newton's second law is the summation of the external forces is equal to mass times the acceleration, and the summation of external forces is all the forces acting on the mass m by other objects other than m. So here's the Atwood machine. I'm going to call this example 1. And the Atwood machine is basically, you can imagine a weightless, frictionless pulley with a massless rope. And really, there's no such thing as all that. But if the weight is much heavier, the masses are much heavier than the pulley and much heavier than the force of friction and much heavier than the string, then you essentially got the same thing. So what I'm going to imagine, in fact, is a big mass here, big M, and I'm doing it in symbols because that's really the holy grail of doing physics is doing it all in symbols, because when you get a result, you get a result that solves all problems like it, not just a particular problem. So, and it's usually easier, in my estimation, to deal with algebra than it is to deal with arithmetic. You've seen the troubles I have with thinking I'm doing arithmetic really well, and I'm like off by a factor of 1,000,000 or something. So I'll put a little mass, little m over here. So as I said, if you really think a lot about it, you could use a Newton's second law the summation of the forces, the external forces acting on a mass m is equal to mass m times acceleration a, you could come up with one equation for this total mass string mass system. And you'd possibly get it right, but it really is not a good way to do it. And again, that precludes your ability to get the tension in the rope, which is part of the problem we're asking. What we want to ask for is, what is the acceleration of this object? Obviously, I wrote a big M here because I'm assuming that's the larger of the two masses, and this is the lighter of the two masses. So what I'm expecting is this large mass to fall downward. Okay. And in fact, since this rope's not going to stretch or become slack, I'm ignoring those types of scenarios. Then every second that you watch this piece of rope, say, it's going to move exactly as far in that second as this piece of rope did. So there's really only one acceleration, and I need not call it a left or a right or ax or ay. I'm just going to call it a. The other question I'm looking for is, I'd like to find out what the tension in the rope is. And oddly enough, this mass M here, this big one, it's going to see basically, if you imagine it's an animate object as opposed to an inanimate object, you would feel yourself falling at free fall. And that's really what you're intending to do. But this stupid rope is slowing you down. So you sort of just see this as gravity pulling you down and a tension in the rope pulling you up. Well, that tension in the rope, I'm arguing, is exactly the same as the tension on this side. Only on this side, notice this guy's like, I'm wanting to fall straight down at acceleration g, but this stupid rope's pulling me up, right? So that's why I'm going to make the tension up on this side and up on this side. But not only that, if this pulley weighed something, then these two tensions wouldn't be the same, because this pulley, the tension on the left-hand side would not only have to lift this mass up against gravity, it would also have to rotate this pulley, which has mass, and would have to rotate this pulley, which has friction, and would have to lift some of the string up, which has mass. So that's the scenario in which T on this side and T on this side are different, is when the thing either has mass, the rope has mass, or the thing has friction. Okay, so really there is only one T as well. So first off, I'm going to write off the left-hand side free body diagram. Okay, and what I'm choosing, I'm going to go ahead and go with the assumption that this big M suggests its mass is going to be larger. Maybe this is 100 kilograms and this is 50. Okay, in that case, I expect this thing to go downward, so I expect acceleration to be positive this direction. So I'm going to choose this direction as positive. So I'll draw on my axis. I'll just draw basically a axis pointing straight down, and I'm going to call that the positive, let's call it the positive y-axis. What the heck? Okay. Now my free body diagram is going to be a mass big M as a dot, and now it's going to have the forces acting on it. The force acting on M, or one of them, is acting in the positive direction, which is downward. And that force is weight, which equals big M times G. Does everybody agree that that's acting downward and therefore in the positive direction? Now, the other force acting on it is the tension T, which is acting by necessity in the negative direction. Hence, I use the red marker. Okay. Now, when you do that, if you really want the best results, it's really wise. I mean, you can work your way out of it if you screw up, but why bother? The best way to work with this is when you choose a direction in the Atwood machine, stick with that direction in a manner that's consistent on the other side. So, for instance, I'm calling this big mass, big M, going downward to positive direction. That's completely consistent with the mass, little m, going upward. So that's going to be the positive direction on this side. That's what I mean. So now I'm going to do a free body diagram for the right-hand side. Now, later we'll actually study torque and stuff, and we can put mass on this pulley and friction on this pulley and even mass on the rope if we really wanted to. That's a little different issue. But learning this stuff now about, you know, keeping a consistent positive direction will make your life a lot easier with that scenario. So now I'm going to draw the free body diagram of the mass M. Now this time I'm saying up is the positive Y direction. So I'm going to put it there. And what I know is in that positive Y direction is a tension T. Again, the exact same tension is over here. And notice it looks like they're canceling each other out. That's sort of what happens when you do your tensions properly in a physics problem. Okay. Now, acting in the negative direction on this side would be the weight of the other object, which I'm going to say is little m g. So that's our free body diagrams for this particular problem. Notice I have two of them. That's what I recommend you doing. Do not try to do it with one equation. It's just going to be ugly, and there's a high probability that you're going to make a mistake. So just don't mess with it. Now I'm going to write out my F equals ma. I'm only dealing with one dimension, so I can ignore the vectors. Really what I'm doing is substituting negative components for the direction. So in the negative direction, the component will be negative, and in the positive direction, the component will be positive. So it'll look like I'm doing subtractions, as I've mentioned to you before, but in reality, it's all additions on this side. It's just some things are negative and some things are positive. So for this one, the summation of forces gives me a mg that's positive and a t that's negative. So I want to say big M G minus T is equal to, now because we've only done one body, it's obvious what the mass is. It's going to be big M times A. Okay, so now the mass was big M. There was no ambiguity in that. That's where part of the problem runs in when you try to treat this as if it's one big object. Now over here, I'm going to do the same thing, only this time you can see mg is the negative thing and t is the positive thing. So I'm going to say t minus little m g. And again, there's only one mass to deal with, so I know the mass is little m, and then we have ma like that. I'm going to call this equation 1. I'm going to call this equation 2. And I think you can see it's a system of two equations, two unknowns, T, A, T, and A. So T and A are the unknowns. And of course, for every unknown, you need a separate equation. Now, this one just happens to be super, super convenient because one of the T's is negative and the other one's positive. So I can add them. So I'm going to add equation 1 and equation 2. And this is going to be easy peasy. I'm going to say T minus mg is equal to ma, and I'm going to say minus t plus mg is equal to big M, excuse me, big M times A. I can't stand that ugly M there. I know this is wasting your time and mine, but here I am. I'm on medication and everything, and I still do it. Of course, y'all see how successful I am. All the success I owe to my OCD. All right, and so now when I add them, you can see the T and the negative T cancel out. I'm going to go ahead and factor out a G on this side because I'm like super awesome ninja algebra dude. So I'm going to say M minus little m times G is equal to, and I'm going to factor out the A too again because of those ninja skills I told you about. It's M plus M times A. Okay, so now you can see easily I have an acceleration, and that's equal to M minus M over M plus M. Notice that quantity has no units. This is a thing us physicists like to do. We like to write an answer in terms of something with no units times one thing that has the unit that we want. So that's why I wrote it that way. No units. This clearly has the units of acceleration because it's gravitational acceleration. So I know that A is in fact the difference in the masses divided by the sum of the masses times G. Now, one thing you should inspect with this is what happens if I were to cut this rope? What would that be equivalent to? What would little m be if I were to cut this rope? Anyone? Seriously, I know you guys can answer this. Imagine cutting this rope right here. What does little m all of a sudden become for this problem?
Gravity.
The little m, the mass, wouldn't that be equivalent to a certain number for kilograms? I think you're answering the question that's maybe 2 questions ahead of where I'm going, or where I am, I should say. So when I cut this would be just like this object with no mass, because remember the string has no mass, the pulley has no mass. So without this mass on the other end, this thing's just sitting there and you're going to let it go, right?
Little m becomes 0.
Exactly. So if you take the limit as little m goes to 0, that part right there disappears, and m over m is just 1. So you see, you would expect this thing to fall at gravitational acceleration, and this gives you that result. That's one of the things you should do when you get a physics answer at the end, is try the extreme conditions. You know, if you're dealing with an inclined plane, maybe let that inclined plane angle go from 30 degrees to say 90 degrees and see if it comes back and gives you the Atwood machine question or answer. So that's sort of the kind of stuff I want you to always think about after you solve a physics problem. Does it physically make sense, right? What about if the two masses were equal? What would you expect to happen if the masses were equal? Remember, we assumed that the string had no mass. So if you assume the masses were equal, you would probably expect neither one to move at all. And then when that's the case, this equation gives you that too, because m minus m would be 0, so the acceleration would be 0. So those are 2 nice, quote unquote, special circumstances you can test your answer on and see if it makes sense. Now, all I have to do is plug this back into equation 1 or 2, and I can solve for t, and that's what I'm going to do. I'm going to do the 2 one because the t is already positive for that one. So I'll plug this, which I'll call equation 3. I'm going to plug 3 into, let's say, equation 2. Again, it doesn't matter which one you do. I hate dealing with negatives because that means more chances for me to make a mistake. So I'm going to say t minus mg is equal to m times m minus m over m plus m times g. Okay. Now that's going to give me t is equal to m plus, now I'm going to distribute this m through here. I'm going to say m minus m squared over m plus m, and I've also factored out the g. Okay, hopefully everybody can see what I did there. By pulling this mg over there, I had a common g, so I just pulled that out. And what was left of the mg term, when it came over here, it became positive, so it's that m there. Now I'm going to get a common denominator, and I'll see that, notice if I wrote a string of equals here, it would technically not be correct at some points. That's why I often tell you to use the left-hand side, right-hand side notation that I've been talking about. In this case, I just drew an arrow to say this suggests what I'm getting ready to write. And that's going to be, this is equal to m times m plus m, and then plus m, I don't know why I said plus and wrote minus, m minus m squared. Now all of them have a common denominator, m plus m, and all of it's being multiplied by g. Now I can carry out that algebra and I'll get m plus m squared plus m minus m squared over m plus m times g. And I tell you, there's just so much enjoyment that comes from doing this algebra this way. I don't know, maybe it's an OCD thing, I don't know, but I like it. Okay, so now I've got the final answer, and it's going to be kind of neat. Notice the m squareds cancel out because I got an m squared and a minus m squared. So what I'm going to do is I'm going to say this is 2 times little m over m plus little m, which notice that's massless, or excuse me, that's unitless because it's mass over mass. And then I'm going to multiply that by big M G, which has the units of newtons, which is what we expect a tension to be. A tension is a force in a rope, okay? So that's the actual answer for the tension done properly. As you can see, I made a mistake on one of the videos I posted last night. I had actually made this mistake and caught it in real time. But I went ahead and posted on my YouTube channel anyways, in hopes that people could maybe look at it and find out what I did wrong. So I still think it's fairly instructive to look at that even when it's done improperly. And really, it was just a careless mistake where I ignored a plus and a minus sign. But this is actually the right expression. And lo and behold, you're going to see exactly this weird expression, this 2mm over m plus m. You're going to see that other places in physics, just like you're going to see this m minus m over m plus m in other places in physics. So I think it's always useful for us to take the time to solve such a problem once to see that we can get it. So you all should be able to, at this point, put your notebook down and draw the Atwood machine. You can use masses and numbers if you want, that's fine. And then solve this and get exactly these expressions. Now, I would say maybe you need to do it with the numbers first just to get used to it. But if you can, ideally, I'd like you to get to the point where you can do it with your symbols like I did. So that's a really good problem. You could, again, evaluate certain things like what if m was 0? Well, if little m was 0, you can see again, this m up here is going to become 0. This one's going to be 0 too. That's not going to matter, but this one being 0 is going to make the tension equal to 0. And that's exactly what you expect. Where the rope isn't pulling up on the little mass little m anymore. So you would expect the tension to be 0 in the case of that. Okay. Also, if the two masses were equal, then you just get 2m, that's 2m squared plus 2m, over 2m. So clearly you would get that the tension is just mg, which is literally the weight of one of the objects. Okay. Notice if the big M was replaced with little m, then all of them would be equal, and I have 2m over 2m. That's going to cancel out, and then I'd have that same little mg. That's what the tension in the rope is. It's what's necessary on the left-hand side to hold up the mass mg, and then on the right-hand side, it's what's necessary to hold up the mass mg. So you get mg. So that's, again, evaluating the final answer to make sure it makes sense. Any questions on that? All right, so let's look at next, which is the next step just before another Atwood machine, is just look at a mass on an inclined plane. So let's look at example 2. I'll put a line here to demarcate it. Okay, so an inclined plane, basically, remember that's a simple machine that we learned about in grade school. You can say it's a block, a ramp, or something like that with a non-horizontal surface. And on that block, we can put a mass m. Okay. And we know if there's no friction, we know this block will actually slide down that incline. And if there is friction, if this angle is big enough, it'll still slide down the incline, right? That's more or less what a slide is at a playground. And obviously a slide's made to have a little bit of friction, as little of friction as it can, so that you can actually enjoy a fast slide down the slide. So what we want to do is now analyze what is the acceleration of this object, assuming friction is 0. So F is equal to 0. Remember, that's the symbol I use all the time for friction. So if I write F equals 0, what I'm saying is we're going to assume this is a frictionless scenario. And you might wonder to yourself, well, wait a second, why does the block slide down the incline? I know the force acting on it is a normal force, and the weight of gravity, well, gravity points straight down. It has no component going to the right, and the normal force is completely perpendicular to the surface. So it's almost like there shouldn't be any vector force pushing it down the incline, but in fact there is. So let's draw our free body diagram. So this is the case like we were just talking about with Gavin's problem. I'm going to tilt my axis like this. I'm going to say my x-axis is tilted at theta degrees, just like the incline is. And my y-axis is, of course, 90 degrees from that.
You're writing.
I'm writing outside the board. Thank you. Thanks for catching that. So my x-axis is over here. My y-axis is over here. I've defined this is the positive direction. That is the positive direction. And this is my mass M right here. Now, the forces I have acting on it are positive forces. For instance, I have this positive force right here, which is the normal force. Remember, I told you I usually use F with a subscript N. Sometimes I'll use just N by itself. And some books will use just N by itself. The other force I have isn't really along either of those axes, so I'll just draw it black. And that force is M times G. Now I'm going to complete my y-axis this way and complete my x-axis this way, sort of, just to show roughly where it is. Now, if you realize that this angle right here is theta, then I think you'll see that this angle up here, notice it makes a triangle all by itself. So if this were 30 degrees, this one would have to be what? Remember, this is a right triangle.
60.
So yeah, if this one's 30, this one has to be 60. So that's 90 minus theta, in other words. And then notice this angle is the x-axis, this angle is the y-axis, so that total angle must be 90, right? So what must this angle be?
30.
Exactly, back to 30, which is what theta was. So that's a key point to understanding how to do this type of problem, is you've got to figure out that that is the angle theta, okay? Now what we're going to see is we have a negative y component for the weight. That is this. So this is weight sub y. Now we have a positive x component though for the weight, and it goes, of course, parallel to the x-axis, and that's weight sub x. That is actually the force that forces the block down the incline. Okay, and notice this is just like the problem you were just asking about, Gavin. Notice if I want to make components of a vector that ends here, I have to start at the tail and walk a certain direction along one axis. The head is the direction I walked, and then I got to go from the head of that one parallel to another axis. And again, the head is where I walk. This head is pointing in the positive direction, so I'd call that a positive component, whereas this head is pointing in the negative direction, so I'll call it a negative component. So I could write over here, just to be complete, that WY is equal to negative mg cosine theta, and that WX is positive mg sine theta. And if you watch the first episode of Big Bang Theory, you will learn that Leonard gets roped into taking a TV up to Penny's room, and they estimate that the angle of a stair that they got to slide the TV up is 30 degrees. And then they say the force is mg sine theta, and theta being 30 degrees, that's about 1/2 the weight. And of course, Sheldon says, it's exactly 1/2. So, but the interesting thing is they did use mg sine theta, right? That's exactly what the force up an incline is. So that's kind of interesting. Now I can discover what the normal force is, and I can put that as an extra. Let's pretend like we wanted to know what the normal force was. So we're going to see yet another instance where the normal force is not the weight. So I take the summation of forces in the y direction, and often we'll call this, for instance, y prime and x prime. Then I'd say the summation of forces in the y direction prime. That's equal to mass times acceleration in the y direction. But we're not imagining this block bouncing up and down the incline. It's just going to slide down it. So that acceleration should be equal to 0. And lo and behold, we get F normal, which points upward, minus mg cosine theta is equal to 0. So that tells us the normal force is mg cosine theta. So that's one thing we've solved. And that's actually true, the normal force. And for instance, if you have an inclined roof, as most people do, that is the force that you have to deal with when a person sort of is walking on the roof or whatever, that's the one that actually stresses the beam perpendicular to the beam is mg cosine theta. Okay, the mg sine theta actually compresses the beam. So now let's do the other one. The summation of forces in the x direction equals mass times acceleration in the x direction. That's really the only acceleration. So I'm just going to call that plane A, like I did up there. Now I just put all my forces in there, and I can see the only one acting in the x direction is this one, which is the mg sine theta. So I'm going to say mg sine theta is equal to m times a, or a is just equal to g sine theta, and that's exactly right. So that's the acceleration an object gets, again, assuming friction is negligible. Any questions on that? Now you can do exactly the same thing. Let's draw one more line. I'm actually going to fit this on the same page because I think I can do it without writing little. This is going to be example 3, and this will be an inclined Atwood machine. So the diagram is going to be kind of small, but we've already worked out the diagram, so it's really not that big a deal that it's small. I'm going to put a little pulley up here on a rod, and that rope is going to come perfectly parallel to the top surface of the incline. In other words, the angle. That's going to be M. Again, I'm assuming negligible friction, and I'll put a mass big M over here. The big M suggests to me that it's going to win, and this way is going to be positive. So I'm going to go ahead and do that and say this is the positive y direction. And then that means going up the incline is going to be a positive direction as well. So my free body diagrams are M with a tension acting in the negative direction and an mg acting in the positive direction. And then my other free body diagram is the same diagram I had before, except now I add a tension to it. So I'm going to say it's this little dot, and the axis is like this, and this, and this. Only this is my positive x-axis now, or positive y, I should say, just because I'm saying like the y-axis turns and turns like that. So you can play with that all you want. The main thing is now we've got a positive normal force like we had before. And we have, in fact, a positive tension on this side. And we also have a negative component of weight. That's W sub Y, exactly the same as before. That's M, little mg. Okay. Everybody sees what I'm doing there? Everybody got that? And then, of course, the component going downward is a negative direction as well in this coordinate system. So this is WX. So we've already worked out the details for the perpendicular direction. So really all I care about is this direction and, of course, this direction. So for this one, I'm going to get mg minus t is equal to big M A. And all I want to know again is A equals question mark and T equals question mark. This one gives me T minus mg sine theta is equal to MA. So this is going to be equation 1. This will be equation 2. I think you can see what we're going to do again. We're going to add them. So I'm going to say add 1 and 2, and you will get, of course, M minus M, or let's do this. I don't like the way I was writing that. I'm going to write it as succinctly as possible. And basically what we're going to get is mg minus mg sine theta. So that's going to be m minus m sine theta times g is equal to m plus m times a. So you can see immediately the a is equal to m minus m sine theta over m plus m times g. And again, I've gotten it written in that format that I told you we like to write as physicists, where it's, you know, unitless times something with the right units. And not only that, you can examine the case where theta equals 90 degrees. If theta equals 90 degrees, that better be just a normal Atwood machine, because now the Atwood machine is vertical. So you have two masses hanging vertically from a inclined plane. And in fact, as theta becomes 90 is in fact just 1. So we get exactly the same expression we had for the Atwood machine when the theta is 90 degrees. So that's a good check on it, right? Now the masses also can't be equal to cause it zero acceleration. The mass has to equal m sine theta. So that gives you a whole nother thing to think about. The tension I'll leave to you, but you can probably guess it's going to have a m sine theta in it and an m plus m in the bottom. So I will leave t equals question mark for you to solve, because we really ran out of time. And I think that's, you know, pretty straightforward to do. All you really have to do now is plug in a that you just solved for here, but you can see that extra little sign turn. That's really just going to add something to this. So I suspect you're going to get 2m sine theta over m plus m times big M times g. So I'll allow you to do that algebra yourself for the fun of it. And of course, you can always check it just by making sure that the tension becomes either of the masses, either m sine theta or big M times g when the two are equal, and that as little m goes to 0, you should get 0 tension. And that should probably be enough for you to verify that your answer is somewhat correct. But anyone have any questions, you're welcome to stick around. Otherwise, you're free to go. We have finished chapter 4. We'll introduce friction next time. And don't forget cadmium. You wanted to talk to me about something, so.
Yes, sir. If no one else has any questions, my email to you was
I'm reading it
about.
right now.
Huh?
I'm going to read it right now. I can pull it up right on my phone. That's what I want to do, so you don't have to say it out loud or anything. And I'm just assuming it's, you know, none of anybody else's business. So, so I'm just going to read it real quick.
Oh, okay.
Oh yeah, and you go by Shannon, don't you?
Cadmium is my preferred name, sir.
Gotcha. I'm just saying the email comes up that way. My fault. I will call you cadmium.
Oh,
good. There it was on the needed include calculation for pi. Okay. So this was 99. I got a question about your calculation. You said you noticed my comments about your lab. Is that the email you're talking about?
Yes, sir.
Okay. Oh, okay. I thought I even put a mark by this on my email, so I did read it. I thought I'd replied to you, but I hadn't. I will take care of that. You re-uploaded it, but you did so before the due date, so I might have looked at the old version. Is that what you're saying?
Possibly. The new one that I had uploaded was right after the lab on September 3rd.
Oh, okay, gotcha. Yeah, then that still would have been technically late, but yeah, I can give you at least the credit back for the lost points for that, leaving that out. So yeah, I'll fix that for you.
Thank you, sir.
No problem. And hey, remember, if it's still not 100 after I correct that, you can still resubmit it, and I'll give you halfway back what what the points you lost were.
Thank you.
You're welcome. Thanks for letting me know. Anybody else have any questions?
I'm just still writing down what you have there on the paper.
No problem. So yeah, that's a neat little problem. We're going to build on this over and over again. You can have double incline planes. You can have incline planes with a pulley that has friction, with a pulley that has mass. You can have double incline planes with two different coefficients of friction. There's all sorts of ways we can build on this. And you'll look, even though they exclude friction, you'll look in the problems at the end of the chapter for chapter 4, and you'll see a bunch of different problems like that. So if you need more practice, by all means, take the time to look at it and see if there's anything you can do to get that, to solve those types of problems. Because if you can do those, you can do just about anything for chapter 4. Anybody else have any questions about this or otherwise?
I think I might be having a little trouble kind of conceptualizing that last bit, the example 3.
Okay. Yeah. So what we have here is an inclined plane.
Do you have another class that you need to go for, by the way?
No, not this time. I got actually a nice little break. So, well, a whole 30 minutes of a break.
Oh,
So,
all right.
but it's for our meeting, so it's not that big a deal. This is a mass M sitting on an incline. Just like that, it has a component of its weight pulling down, so it has a tendency to slide down, just not as big a tendency as this mass
As
has.
just straight down, yeah.
Yeah, so that's sort of the big deal. This one's just like the left-hand side of the Atwood machine. So you get a mg minus t is equal to big MA. That's what Newton's second law says. This one, instead of having a t minus mg, you have a t minus mg sine theta.
One sec. So that the number 1 equation that you wrote on the left, that's
Newton's second law.
Like where is that being applied on the equation exactly?
Okay, so remember Newton's second law is the summation.
So basically all that's doing is that g is the acceleration due to gravity, a is the acceleration of the object itself after you take tension into account.
Oh, well, this side, I'm scared by what you said about g. This side is that. The total forces acting on the mass M are its weight pulling down, which is a positive direction, so I wrote it as mg, and its tension pulling up, which is a negative direction, so I wrote it as negative t. So that left-hand side is really the summation of the forces acting on big M. The right-hand side is just ma.
All right.
That's a good question. A lot of people get confused and they think I'm jumping ahead in algebra and they think this mg might be part of the term over here, and that's not it at all.
Okay, so I got that one. That's it's the right side of that equation anyways. That is the large mass and the acceleration of the large mass.
Right. That's the right hand side of Newton's second law.
Yeah. Okay.
The same thing's happening with this guy, only this one, instead of having mg, has mg sine theta.
And so it's t minus it's t minus mg sine theta because tension is greater, since the mass on the other end of the pulley is going to be greater.
That's not why. In fact, the two tensions are equal. The reason is, when I decided that this was a big M, that made me think, okay, this one's probably going to be the one falling. In other words, it's going to overwhelm the force of the weight on this one trying to slide it down. So I suspected it was going this way. I didn't want my acceleration to come out negative, so I chose this to be the positive direction, that to be the positive direction on that side. But if I move this, a certain number of meters in a certain second, then this is going to move the exact same number of meters in that same second this way. So this way's got to be positive as well. You can sort of picture it like the y-axis is pointing this way and then coming back down and pointing this way over here. I'm trying to keep those consistent, because if those signs are different, you're going to run into some algebraic problems and really some confusing stuff that makes your life a lot harder. You can still work it out, but it's not good practice.
All right. And so since moving towards the pulley is considered the positive direction, you're having the tension be positive?
Yes.
Okay.
And the mg sine theta, that of course is more consistent with the big M going up, so that's why it's negative.
Okay. And so the MG, so what we were doing with the with the combination of the vectors on that, it's basically the normal force. It's the normal force, vector combined with the, straight downward force. So what one can assume, at least in this situation, that the normal force is going to be equivalent to the normal force is going to be equivalent. So and this is also going back to the tilted axes thing that I was asking you about.
Right.
The normal force is going to be equivalent to the y component of the like the gravitate, like the force
The
due
weight.
to gravity
Right.
on that tilted system, leaving only the x component. And
Yeah.
that is what you get when you do the mg sine theta there.
If I took, now this was just for one axis. Notice this is two-dimensional. I've got this axis, which is the one I chose to solve, but I also have this axis, which is another F equals MA I could work out. I chose not to do it because I can see it's identical to the one I did up here. So I already know the normal force is mg cosine theta.
Well, yeah, and that's what I was talking about. The normal force is going to be equivalent to the
Y component.
y component of the gravitational force.
Exactly.
And so you don't really need to calculate those, I guess.
Exactly. You will when we start to bring in friction, because the normal force is or the friction force is proportional to the normal force. So next chapter we'll need that. And now you're in a place where
Okay.
you know how to do it. And that's why I was doing all this about the normal force. So that's one of the reasons.
Gotcha.